Hey guys, it's Coach Sam here, and in this video I'm going to be explaining how to make your robot drive perfectly straight using Python. So we're going to be using a Spike Prime robot such as this, and we're going to be using the Spike Prime app. However, we're going to be coding in Python. So Python is a very powerful language as we've already discussed. However, everything you can do in Python, you can also kind of do in word blocks. So if you're starting out this programming and you haven't really used a gyro straight or other sensors before, I definitely recommend first going into the word blocks. I've got a video up on the exact same thing in word blocks. So learn that, and then coming back to Python, you'll be a lot more skilled. However, if you're ready to go, if you're confident, definitely stay on this video, and we'll learn how to actually program the robot using Python. So this video is going to be sectioned into 3 different parts. So after this introduction, I'm going to be giving a brief explanation into what the gyro straight is. Understanding exactly the logic behind the program is very, very important, and it's actually more important than knowing what the program actually is, the code itself, because once you understand the logic of it, you can complete this without this video. You can actually create the program by yourself. So it's very important to understand how it works, so definitely continue watching onto the explanation part. However, I'll also put timestamps below. In the third section, I'll actually create the code. So if you want to skip straight to the code, you can do that. However, I highly recommend watching the explanation. So without further ado, let me now explain what the gyro straight actually is on an iPad. Okay, so we're here on the iPad, and now we're going to very briefly just explain the understanding of what's going on with this gyro straight. So to understand, the gyro straight is a solution to a problem, but what actually is the problem? The problem is when the robot is moving. As you can see, I've got like a little sketch here of the robot. When the robot's moving, we want it to stay on this 0 angle, as you can see over here. So when it drives, just with the basic, purple blocks, it'll drive like this. And slowly, it'll, start to veer off track, right? And it'll go, quite different to its destination. So if its destination is somewhere over here, it may actually end up somewhere, to the left or to the right. Now, this is quite exaggerated, but the fact is, over different straights with different turns, this can, this inaccuracy can really add up. So what this is a change in angle, right? So instead of landing on the 0 angle, it deviates by about 2, maybe 3 degrees. And this is calculatable. Like, you can take this number and you can calculate it, and we'll get to that later. But let's think about why this happens. So why is there a actual deviation, or what we call this is veering? Well, it veers for a certain number of reasons. There are actually a few. The weight imbalance. So that's the first thing. If you have more weight on one side of the wheel than on the other side, then it will veer toward the weighted side because that wheel applies more force to the ground. Traction slippage. This is similar to weight. So sometimes what can happen is this wheel will actually slip from the ground because it doesn't maintain its traction, its friction with the surface. And the last one is power discrepancy. This isn't as much of an issue with Spike as it was with EV3, but sometimes it can output, the hub can output different powers to the wheel. So one wheel may actually be turning at 94, 93, whereas the other one's turning at 100. And so that power discrepancy becomes a bit of a factor. So these are 3, main factors. And that's the real problem, right? We now need to fix this. So how do we solve this? I said that, we can calculate the angle of the deviation, and to do this is with something called yaw. So yaw, you can think about yaw as angle. When I say yaw, I just mean the angle of the robot. So right now, like we had the example last time, if this is 0 degrees, then the yaw angle here is simply 0 degrees. Okay, over here, right? I'll do this example next. Over here, the robot's actually turned. So before it was like this with the wheels like that. The robot's actually turned about 90 degrees, right? So the yaw angle here would simply be 90 degrees. Now we have somewhere here, this is somewhere in the middle, this case over here. So, I haven't calculated this with a protractor or anything, but we can roughly say that yaw angle here is 45 degrees. It's somewhere in between 0 and 90, right? And it seems like straight through, the middle, I guess. If you were to put lines here, if that's 90, it seems about halfway through 90, which is about 45 degrees. So that's where that comes from. And that is the yaw angle. So with the yaw angle, all you need to know, the angle of the robot is simply the yaw angle, and we can actually calculate this. So there's an internal gyro sensor in here, and what this does is it'll take the input of the position, it'll set it at 0, and then if it deviates, which you can see here, it's actually able to calculate, I've deviated 2 degrees. So what we're going to do is we're going to use the internal gyro sensor, and we're going to use some mathematics and some programming to actually fix it, and that's where the gyro straight comes from. So a little note over here. pitch and roll can also be calculated. So yaw is basically the angle side to side like this. Pitch and roll are just the angle like this and like this, right? This is why you may have seen the specifications. This has a 6-axis accelerometer, which just means it can calculate not only with these two axes, there's this axis over here, these two, and these two over here, but it's highly unlikely your robot in an F-law competition is gonna go like this, right? Which is why it's only, you know, very important for you to calculate the yaw angle. So we can pretty much disregard pitch and roll, but they can also be calculated, and it's important for, you know, other fun tasks like balancing and whatnot. But anyways, now we get to the crux. So essentially, we're going to follow a rule. This rule is going to be the correction is going to be 0 minus the yaw angle. Now this may be a little bit confusing, so let's do an example. We said this is the robot, okay? And the robot, it'll start. So this is without the gyro straight. The robot will start and it'll veer off track. So we have a little slight veerage over here, this, you know, deviation. Let's call this 2 degrees. Let me make that a little bit more neat. So this 2 degrees is calculated by the yaw angle. So the yaw angle right now is actually 2 degrees. So what we're going to do is we're going to do some math. We're going to go 0 minus 2 degrees, and that follows this rule over here. As you can see, this is the correction. What's 0 minus 2 degrees? Negative 2. Okay, so then what it will do, will then steer back, right? Like that. And because, you know, the reason why it does this is because you've gone off 2 degrees, the robot now wants to go 2 degrees back on track. That's the basic idea of the gyro straight. It'll take the error and it will do the opposite, like it'll minus the current position with the yaw angle, and it'll minus that and it'll do the opposite. So it's gone back off track, now it's minus 2 degrees, and now we're back on track, right? So let's say it's going now, it's going fine, and then we'll veer this way. If this was 2 degrees, let's say this is maybe negative 1 degree. Okay, the rule also still applies, right? So the rule is the correction equals 0 minus the yaw angle, which is 0 minus, and then we have negative 1. And that equals 0 minus minus 1. These two negatives make a positive, which is 0 plus 1, which equals 1 degree. So it veered off negative 1 degrees. It's then going to go back by 1 degree over here. This is the basic idea of the gyro straight. This is what we call proportional logic. Now, that's just the name of this. You know, essentially this is essentially a proportional logic, right? The rule that it follows is called proportional logic, and proportional logic is used in a lot of different situations in real life. It's also used not only in gyro straight, but also in the line follower, which there'll be a video about that as well. So it's very important to understand what proportional logic is. In essence, whatever mistake the robot makes, we're going to do the exact opposite to get back on track. That's all it is, really. Fundamentally, it's just proportional logic. Now, there is a, you know, small, update that we haven't really explained. Basically, what we do is we take the correction value. So this correction over here, we take the correction and we multiply it with something called the GSPK. So I'll briefly explain this because it's quite important and it comes up in the program. The GSPK is called the gyro straight proportional constant, but simply it's just a number, right? What this number does is it controls the rate of corrections. So let's just say the correction for whatever number it is, let's just say we're going to do correction multiplied by 1.5. So this is going to be situation 1. And then situation 2, we're going to do correction multiplied by 0.5. So the GSPK is just a number, and I've chosen 1.5 in situation 1 and 0.5 in situation 2. What is this? Well, let me now explain the difference between this GSPK, the high and the low. So as you can see, we have a bit of like a curvy fashion with the gyro straight because it maintains its straightness, right, by going back. With a higher GSPK, what it will do is it will actually do more of like sharper corrections like this, right? As you can see, the corrections are very sharp and there's a lot of different like wiggles, right? With the robot, it goes like this. And that's what a higher GSPK does. It increases the rate of corrections. What does a lower GSPK do? So I'm going to choose a different color. Let's go with green. A lower GSPK will kind of make it a lot more curvy like that. So the purple is actually situation 1. So I'll highlight that like that. And the green is situation 2. So with a lower number here, it has more of like a slow rate of correction, and with a higher number here, it has a much faster rate of correction. Now, if that doesn't really make sense, it doesn't matter. All you need to know, higher GSPK, faster corrections, lower GSPK, slower corrections. That's pretty much it for the understanding. So if you have understood that, then you're pretty much ready to program. If you haven't, maybe rewatch it, ask questions down in the comments below, and I'll try to get back to them. So without further ado, let's go over to the laptop and actually program this out. Okay, so back from the explanation, we're gonna actually do the coding section now. So I've got my laptop open up here. I'm gonna go to the Spike app, and as always, new project and Python. And let's create. So you probably already seen, we're gonna close the knowledge base because I've got everything I need over here. And you've also got everything you need in this video. So we're gonna keep these 3 lines as always, but we're gonna delete the number 7. And the first thing we need to do is initialize our components. So if this is the first time you're using Python, I definitely recommend watching the video I made before. It's called Basic Movements Using Python. I'll link it up here somewhere anyways. But watch that before you watch this, because that will give you an explanation on what you need to do. If you already know what you're doing, then I'm just gonna push through some of the initialization. So obviously our first section of code is going to be initializing our components. I will definitely have typos, probably, in my code as I'm rushing through. But it is what it is. I'm not going to put a space, but it's up to you. You can put a space here if you want to. I'll just leave it with that one. So we've got our hub. Now we're going to actually initialize our motors. So we actually need to initialize 2 different things. We need to initialize one motor like this, motor, and then motor bracket, comma, bracket, comma, A. So this is just the initial motor. And then we also need to initialize our motor pair. So we're gonna go motors. Don't get confused. This is just one initial motor. This is now, we're gonna initialize both motors, and we're gonna use the motor pair command, which we also discussed in the previous video. So I'm gonna go A, comma, E. Okay, perfect. So what have we initialized? We've initialized the Spike Prime hub. This is very important because it's the control system of the whole robot, and it's automatic. We've initialized one motor as motor A. So whenever we say motor, we're referring to motor A. Whenever we say motors, we're referring to both A and E. Why is this important? Because sometimes we may want to use both motors at a time. Other times we may want to use just one motor, which is motor A. So if you want to initialize more things, you can go ahead. However, for Gyro straight, this is all we need. Now let's move to the actual bulk of the code. So with our second section, as always, we're going to put a comment, execute code, because this is what's going to actually work for us. Now with our code, because we're using the Gyro straight, it needs to be set to the 0 angle all the time. So there's actually a command for that. It's a little bit, you know, I guess you can say, it's a little bit tedious. Hub.motion underscore sensor dot reset underscore your underscore angle. Okay, this hectic long command, hub.motion underscore sensor dot reset your underscore angle. Perfect. What this will do is it'll tell the robot whatever position it's in currently is the 0 position, and it's going to go straight from that point. You can imagine if 0 is over here and the robot's now turned, and it thinks that's 0, the Gyro straight is going to want to move back to that angle. So setting it at the start of the program at whatever its position is very important. So the next thing we need to do is reset the actual degrees, because if it's already done 360 degrees in the program before this, it'll just think that it's finished, right? So we need to reset the degrees that it's run. So motor dot set underscore degrees. Again, this is just another command. You can find all of this in the knowledge base. However, I've got it here just to memorize, just from quick access. If you want to know where it is in the knowledge base, it's probably somewhere in motor pairs, this kind of thing. Start moving, stop moving. Or if it's not there, then it may just be in the singular motors. Anyways, so if you got this video, you don't really need the knowledge base though. So the first 2 things, reset our angle for the gyro sensor, and then reset our motors to make sure it's 0 degrees. Now we're all set to actually code the Gyro straight. And the Gyro straight is essentially going to be in a loop, in a while loop. A while loop will continue in action until the until like a certain command has told it to stop. So what is this? Let me write out the code and then I'll explain exactly what this is. So while, you'll see while is a special word, so it comes up in blue. Motor dot get underscore degrees counted, brackets less than, I'm going to put a space just for neatness, 400, comma. Alright, don't forget this colon, this double dots. It's very, very important. What this will do, this is the while loop. So this while loop, everything underneath it will run until the degrees is less than 400. Now you may be like, shouldn't this be greater than 400? Not really, because this is going to continue until 400 degrees has been reached. So while the motor is less than 400, while the degrees counted is less than 400, keep running, keep running, keep running. Then when it hits 400, then you stop. That's why this is less than. So you can think about this sign as the opposite of what you actually want to do. It's a little bit trippy like that, but it's fine. Just remember that it's less than, not greater than, for going forward. Now, what's below it? If you remember to put this, if you don't put this colon in, the next line will just be regular. However, if you forget, make sure you always put it. And you'll notice that we have like a new kind of set. It's actually tabbed in. This is because everything in this while loop needs to be spaced inwards. So make sure this spacing comes up and you know you're on track. It's automatic anyways. So what we're going to do is we're going to set up a few different parameters. So first things first, let's set up something called the GSPK. Again, I'll explain this later. Let's make that one. Let's set up steering equals. I'm not going to put steering in yet. And then we're going to put motors.start steering, which is just this thing if you've written it correctly. Make sure it's exactly the same, steering. And then -30. Alright, perfect. Okay, so what have we done? Basically, we've set up the initial loop in here. As you can see, we haven't put anything for steering in yet, so let me continue what this is. This is the action, the steering is the main command. So it's going to be 0 minus hub.motion underscore sensor dot get your angle, and then we're going to put like that. We're going to put another one here. Perfect. Multiply that by something called the GSPK, and make sure this GSPK is the same as that GSPK. Alright, perfect. So seems like we're more or less on track. Let me explain what this means. If you watch the explanation, you'll know that gyro straight, it works off an error. So once it starts veering, the yaw angle will be able to calculate how much that veer is. So if it's gone off by 2 degrees, it'll say you've gone off by 2 degrees. What we do is we do 0 minus 2 degrees and get -2. And that will go into steering and it will steer back -2. That's how the gyro straight works. So it's proportional. It works off the error to go backwards the exact same amount and go back on track. How does this relate to the code? We've got 0 here. This whole giant command thingy over here, this is just the current yaw angle. So you can see hub motion sensor, get your angle, get the current angle of the gyro, of the yaw. So that's all this does. And then what we do, this is all in one big bracket over here, so don't forget that second bracket. We then multiply this whole steering factor by something called a GSPK. GSPK is called the gyro straight proportional constant. That's a bit of a mouthful. A proportional constant is just a number, right? You can say the number is literally just 1. What this number does is it changes the rate of correction. So I'll do a few tests in this video. As you can see, with a GSPK of 1, it'll just go kind of like a slight curve. With a GSPK higher, let's say 1.5, the correction will be a bit faster. So it'll be a little bit more on track like that. That doesn't mean you can just up this GSPK to like 99, because then it'll just do zigzags and get lost. And it doesn't mean you can put it to really low, like 0.1, because then it won't be able to correct fast enough. This constant is different for every robot. So you're going to need to be doing some tuning to this constant and change it a little bit. So for my robot, I found that 1.4 works pretty good. For your robot, it will probably be somewhere between 1 and 2. Generally speaking, that's how it works. Start at 1.4, you may go up to 1.6, may go down to 1.2. So that's this whole program. However, we still need to do one more thing. So we're going to go enter and then backspace. And we're going to drop one more, motors.stop. Perfect. So this is essentially the gyro straight. All we've done, we've initialized our components and we've set them to 0. And then we've got this loop in here. This loop basically runs the gyro straight. Now, I haven't explained the parameters. So we're running it at 400 degrees. If you want to go higher, make this 600. If you want to go lower, make this 200. Let's test out 1002. So let's put this to 1000. For the GSPK, we've got our 1.4, which I've set for my robot is pretty good. Your robot may be slightly different. And then this motor.start, it'll take this steering command and it'll steer at a power. So we're going to choose a power of not -30 because that would go backwards. Let's choose power of 30. So 30 to 40 is normally pretty good. Pretty much anywhere from 30, 40, 50, 60. Above 60, the gyroscope can get kind of confused and it makes some very fast errors. So try go below 60. But experiment with your robot. The higher this number here, probably the higher the GSPK needs to be. But the lower this number, then the lower the GSPK needs to be. So by changing one variable, another variable kind of changes as well, which is normal in programming. This thing kind of happens. You'll need to fine tune both of them to create the perfect gyroscope for your robot. So let's go with a 30% speed. I'm going to get rid of this backspace because I don't like how that looks. And let's see what this looks like. So as you can see, all it did was a simple gyroscope forward. I'm going to now change this number to something slightly lower. Like let's go 0.5. Let's see what that looks like now. As you can see, the GSPK, because it's lower, it kind of curves back to its rotation, back to its original position. We don't necessarily want that to be too slow. So erring on the higher side is generally a good idea, but not too high. Like if you can test this out for yourself, put this to 3 or 4, and you'll kind of see the robot starts to go a little bit crazy. So anywhere from 1 to 2 is pretty good. I'm going to stick to 1.4. So that was pretty much it. Using this video, you can now know how to use the gyro straight, and you understand how it works if you watch the whole thing from start to finish. So congratulations, this is just the first of many different functions you can use. The gyro straight is what we call a function, because it will go straight. If you want to go straight again, copy paste the same command, it'll go straight again. In the future, we'll learn how to turn accurately. So turning is probably one of the biggest inaccuracies a robot can have, especially on an FLL map. Because you can imagine a 2-degree error of a turn can really add up over time, and it can end up in a different position. So you can also learn a line follower and a line scoring program. So this is just the first of many programs, and hopefully I'll get to see you guys in another video. So that's pretty much it. See you guys again.